Here's problem number 4, sample test 2. A 5 nanocoulomb point charge is embedded at the center of a non-conducting sphere, radius 2 centimeters, which has a charge of minus 8 nanocoulombs distributed uniformly throughout its volume. A shell, radius 3 centimeters, has a charge of 6 nanocoulombs and is also concentric with the other charges. What's the magnitude of the electric field at a point that is 1 centimeter from the center of the sphere? Let's imagine what we have going on here. If we look at a coordinate system here with 1, 2, and 3 centimeters away, we start with a charge at the origin, Q1, equal to 5 nanocoulombs. And then we have another charge distributed uniformly throughout the volume of a 2 centimeter radius. And that charge, let's call it Q2, is minus 8 nanocoulombs. So we have all this negative charge distributed uniformly throughout that volume. And then we have a shell of radius 3 centimeters. And on this shell is a charge, let's call it Q3, equal to plus 6 nanocoulombs everywhere on the shell. And we want to find the E field at a point which is 1 centimeter from the center of our origin. So at point P here. So we can imagine that there's a Gaussian surface 1 centimeter around, and we want to consider that Gaussian surface. We know from our treatment of Gaussian surfaces that any charge outside that surface is not going to contribute to a net flux through that surface, because whatever goes in is going to come out. For instance, for the shell, if it has an E field going through this surface, it will go in and then come out. Hence, there will be no net flux from any charge outside of the surface of 1 centimeter, and hence it won't contribute to the net electric field at that point either. Same thing, so the shell is out of the question for part A. But part of that distributed volume of charge, the Q2 charge, will contribute to the E field, the part that is inside this Gaussian surface. The parts that are outside will not, because that again will create a flux that will go in and then come out, and no net flux through our Gaussian surface. So we want to find the fractional charge due to Q2 that is actually inside this radius. Let's call it Q2 prime. And it's going to be equal to 4/3 pi R1 cubed. I should use the orange for this. 4/3 pi R1 cubed divided by the 4/3 pi R2 cubed of the Q2 surface itself times the charge Q2. Now the 4/3 pi will cancel out, and so this Q2 prime is going to be equal to R1, which is 1 centimeter cubed, over R2, which is 2 centimeters cubed. You don't have to worry about the centimeters because top and bottom, those units will cancel out, times Q2, which is a negative 8 nanocoulombs. So Q2 prime is going to be equal to 8 divided by 8, a negative 1 nanocoulombs. And that will be the charge that is inside this surface due to Q2. We already have Q1, so our total charge inside this surface is going to be equal to Q1 plus the Q2 prime. Q3 is going to be 0, contributing nothing. And so this is going to be equal to 5 nanocoulombs plus a negative 1 nanocoulombs, which would be 4 nanocoulombs. Due to that charge that's inside the surface, which is uniformly distributed and symmetric, it will act like a point charge, creating the E field at point P from the origin of symmetry. So our E field at point P is going to be equal to this kq over r squared, where we're treating all this charge as being located at the center. And so this would be equal to 9 times 10 to the 9 for k. We have 4 nanocoulombs. 4 times 10 to the minus 9 for our charge, total charge. And our distance is 1 centimeter. 1 times 10 to the minus 2 meters squared from the origin. 10 to the 9, 10 to the minus 9 cancel out. And we have 36 divided by 10 to the minus 4. So that's going to be 36 times 10 to the 4, which would be 3.6 times 10 to the 5 newtons per coulomb. Positive, so it'll be emanating away from the center. As we run, it'll be in the positive x direction from the center of that origin. Sounds good. Part B. What is the magnitude of the electric field at a point that is 4 centimeters from the center of the origin? So if we go out here to 4 centimeters, this point right here, let's call it P2. Now, that point, if we were to construct a Gaussian surface here, all the charge in question is inside that Gaussian surface and contributing to a net flux through that surface. So all this charge enclosed is going to contribute to the E field at point P2, and it's all symmetric. The shell and the uniform distribution and the point charge itself are all symmetric about the origin. So all their charges are going to add up and act like a point charge from the origin. So our Q in question here is going to be equal to just simply Q1 plus Q2 plus Q3. And hence, at that point, we are going to have Q1, which is 5 nanocoulombs, plus Q2, which is negative 8 nanocoulombs, plus Q3, which is 6 nanocoulombs, which is going to be 3 nanocoulombs. And that's going to act like a point charge from the center. So our E field at point, let's call it P2, is going to equal KQ over R squared. And that's going to be 9 times 10 to the 9 times 3 nanocoulombs, 3 times 10 to the minus 9, over, and point P2 is 4 centimeters from the center, so that's going to be 4 times 10 to the minus 2 squared. The 10 to the minus 9 and 10 to the 9 cancel out, and so we're going to have 27 divided by 16 times 10 to the 4, which will be 1.69 times 10 to the 4 newtons per coulomb. And as we draw it on the x-axis, it will be emanating outward for the positive charge and the positive flux going through that Gaussian surface. So that will be our E field at point P2, 4 centimeters from the center of the sphere. 1.69 times 10 to the 4 newtons per coulomb will be the magnitude of that field.